Welcome everyone to Colloquium lecture number 2. I'm Ruth Charney, President of the American Mathematical Society, and I will be moderating this session. Our speaker for this second colloquium lecture is again Karen Smith, the William Fulton Professor of Mathematics at the University of Michigan. I would guess that many of you were at her first talk yesterday, so I'm not going to repeat my full introduction. I just want to say that Karen is very well known and highly respected for her work in commutative algebra and algebraic geometry, and we are very honored to have her as our colloquium speaker this year. I would like to remind you that if you have questions for the speaker, please use the Q&A button on your Zoom screen, not the chat. I don't know, given our late start, if we'll have time for questions at the end, but if so, I will be reading them from the Q&A. So today's talk is entitled Measuring Singularities, and please welcome Professor Karen Smith.
Thank you for coming back for more, and welcome to any new people who might have arrived. Sorry, we're getting a late start, and I'll try to do my best to adjust if I can a little bit. So I know there's a lot going on. Let me start my screen share and talk about how to measure singularities. So, sorry, I need to get my pen as well. Okay, so yesterday we talked about singularities of algebraic varieties, and today we're going to talk more about singularities and really how to kind of differentiate them and understand precisely which singularities are more singular than others. So to keep things simple today, we're going to just talk about the zero set of one polynomial. So yesterday we were talking about zero sets of many polynomials, although many of the pictures I drew were one polynomial zero sets anyway. A one polynomial zero set is called a hypersurface. And again, these are familiar things on the screen. I put a few examples. Everything is drawn as hypersurfaces in real space. Of course, as I described yesterday, when we're looking at zeros of polynomials, we want to see all the zeros. So really what we should do is think about zero sets in complex space instead of real space. So we really see all the zeros. So for these, this keeps changing. For these three curves that you see on the top row here, these are all defined by one polynomial in two variables. And this first parabola here is a smooth hypersurface. There are no singular points. This alpha curve here has one singular point at the origin. And this blimp type curve here has one singularity at the origin also. But as you can see, the blimp looks a little bit more complicated. And this is the kind of thing I want to try to quantify today. Similarly, we could have hypersurfaces in R3 or Rn or Cn, even over any field that might be a finite field or something like that. Okay, so how are we going to go about this? What we're going to try to do is focus attention on one point. So we can always change coordinates so that the one point we're focusing attention on is the origin in the space that we're looking at. We just change coordinates to move the origin where we want. So sometimes I'll call the point the origin. And what we want to do, all three of these curves, for example, the origin is a point on them, and we want to ascribe a numerical value to that point that's supposed to tell us how singular it is. And that's the goal, what we're going to try to do today. So the most simple thing you can do, and which might be familiar to some people, is we can talk about the order of vanishing of the polynomial. So we're interested in points on the hypersurface. So we're already talking about points where the polynomial vanishes. But for example, at this point of this alpha curve, the polynomial is vanishing to a higher order. And the order of vanishing of a polynomial is simply the degree of the lowest degree term appearing in it. So this polynomial, we've got 2 terms of degree 2 and 1 term of degree 3. The lowest order part here is all degree 2. So this is a order 2 singularity. Likewise, our blimp, we already see it's more complicated in the sense that it's got order of vanishing 3 at the origin. Now, this parabola, if I look at the origin, the curve has a degree 1 part to it. And this is exactly telling us that we have a smooth point there. Order 1 is the same as a smooth point. And I'm going to skip the proof here because of the late start. But for those of you who saw my talk yesterday and remember the definition of what a smooth point is on a variety, it's pretty easy to see that the order is 1 if and only if the variety is smooth at the origin or whatever point we're interested in. So, so this is a measure of singularity that actually tells us we're singular, that if we're greater than 1, we're singular. And if we're much more greater than 1, we're much more singular. Okay, so let's think about what this invariant means, this order. So for example, for this order 2 curve, this is the alpha curve again here in red. If we think about near the origin, what's happening, these lower order terms, the degree 2 terms, as we take very, very small values of x and y, are going to sort of dominate the story of what's happening with this function, because the higher order terms will be going to 0 even faster. And so near the origin, this alpha curve will look like the 0 set of its lowest degree part. And that's this blue curve here, which is the union of 2 axes. That's the 0 set of y squared minus x squared. So likewise, if I have an order 3 curve near the origin, I look at, I'm going to have 3 tangents. I expect to see 3 tangents, and that's what happens for this blimp. And likewise for this order 8 curve, this lowest degree part here is order 8, and I expect to see 8 tangents. And now what's interesting is we see that the tangents are coming with multiplicities here. If I factor this equation or this polynomial here, I see I have sort of 4 different linear factors, but each is counted with a multiplicity 2. Well, that's because if I look at this flower, if I follow along this branch of the curve, I see that the y-axis is tangent. But also if I follow along this axis, this branch of the curve, I see the y order is tangent. So the y-axis, the y-axis is tangent. The y-axis is a tangent, but it's doubly counted. And so this is basically what this order means for plane curves. It means something a little bit different when we talk about surfaces or 17-dimensional hypersurfaces, but I just wanted to give a little bit of a feeling about what this singularity invariant is. Now, this singularity invariant is not such a great one to really understand singularities. And the reason is, if I compare these 2 curves, so I have 2 cusps, I gave their equations there. One is much more singular than the other, which just looking at it, you can see it's sharper, it's pointier. That's a more singular curve, but they both have order 2. The lowest degree term of the equation defining it is 2, and there's the 2 branches giving us the 2 tangents that come together. The x-axis is a tangent of multiplicity 2 in both of these. So just to sort of justify a little bit better what I mean by the curve on the right is more singular. Intuitively, you see it's sharper. But also, I like to brag about my students' work. So these students on the screen are no longer students. Juliet and Robert are both postdocs, and Molly's a software engineer. But when several years ago, they worked on a project where they actually explicitly computed a resolution of singularities, and they gave a nice algorithm for these kind of curves. And using their algorithm, you can see that there's a much more complicated resolution of singularities for the sharper cusp. So this can be made very rigorous, and they did for these kind of curves. So since the order of vanishing is not the best of invariants for singularities, it's just one, we want to introduce something more refined. And so I'm going to introduce a more subtle invariant or measurement of a singularity or a point on a hypersurface. So for this, we're going to use a little bit of analysis. What we're going to do is we're going to consider our polynomial f, which is defining a hypersurface. So here, the zeros of f are a hypersurface in Cn. And I just kind of drew a little reminder here that we're interested in the zero sets of f. But in my picture, it looks like I'm in C2, and we might be in a much higher dimension in general. And what we're going to do is we're going to consider this function the way an analyst might, where we're just going to take 1 over the norm of f squared, or you can think of it as f times f conjugate. And this is a perfectly good function everywhere except where f vanishes. If f vanishes, of course, this is undefined. It's blowing up to infinity. So this is a function which, in this cartoon-like picture here, we see there are some points where it's not defined at all, namely exactly along the hypersurface that we're interested in. Now, if we have a singular point or a higher order point, a higher multiplicity point on that hypersurface, it's going to blow to infinity even faster. The order of vanishing is going to be higher, and so it's going to explode to infinity even faster. And the question we want to ask is, fixing a point on the hypersurface. So in the picture here, this is just kind of a cartoon. Cn is this plane, and what you're seeing here is the graph of this function, 1 over absolute value of f squared. And so the hypersurface in this picture is really just the point where this is exploding, because I can't draw it any better than in R3. But what we can do is we can ask the question near P, if I take a little ball in Cn, in R2n, and look at the graph of this function just around that ball, do I have a finite volume under that graph or not? And this is something that you do when you teach Calc 2, or Calc 2 students do. They study sometimes how to dampen down a function that has some kind of asymptote to make it have a finite integral, a finite volume under the graph. And so what we're going to do is we're going to dampen down this function by raising it to some positive lambda, and we're going to figure out for what lambdas do we have a converging integral. Is that volume finite? So just to give some examples and to try to convince you it has something to do with singularities, let me point out that if we have a smooth hypersurface, and so I can change coordinates, so I can think of the f itself as a coordinate, and I can compute the integral. It turns out that this integral will converge if and only if lambda is less than 1. This is a kind of an exercise that might be on a qualifying exam for an analysis PhD program, a qualifying exam in analysis in a PhD program. Not too hard to check. And similarly, using Frobenius theorem, we can check when an integral for a polynomial that looks kind of like a monomial in the coordinates converges, and we get a value for when it converges, which I've put on the screen. So in general, when I have a smooth function, this integral is going to converge for lambda less than 1, and it's going to diverge when lambda is greater than 1. And if I have a more singular point, I expect to take a lambda to be smaller in order to get an integral to converge, to get the integral to converge. So this leads us to an analytic index of singularities, an analytic measurement of a singular point on our hypersurface called the log canonical threshold. So the log canonical threshold is just the cutoff point where the integral converges for lambdas less than that and diverges for lambdas greater than that point. And these three facts here highlighted in blue are not too hard to check, or they're I guess more or less clear to probably most analysts, that an arbitrary point on a hypersurface will always have log canonical threshold 1 or less. 1 is kind of the best we could have, because that's what happens when the hypersurface is smooth, or when the point is a smooth point on the hypersurface. And in general, if I have a nastier singularity, higher order is going to have a smaller log canonical threshold. And the more complicated and nasty it is, the more we expect to have to dampen down that function in order to make the integral converge, to get a finite volume under its graph. So I want to point out, unlike the order, the log canonical threshold is not telling us, it can't detect when a hypersurface is smooth. It will be 1 if a hypersurface is smooth, but it can be 1 even when the hypersurface isn't smooth. So for example, for the cone, the vertex is a singularity, but it's a singularity of log canonical threshold 1, same as a smooth point. So connecting to my talk yesterday, we saw this cone was something we called a rational singularity, kind of a barely singular singularity, a negligible singularity. And this log canonical threshold, when it's 1, it's also telling us we have kind of a negligible singularity. Okay, so let's see if this does any better on our cusps. And in fact, it does. If I compute the log canonical threshold, of course, at the singular point, at the origin, the log canonical threshold at any of these smooth points is going to be 1. But if I compute it at the origin, look at a little integral, I look at a little ball around the origin, compute that integral, figure out when it's finite, I get different numbers. And notice I get a smaller number, 1/2 plus 1/17, for the sharper cusp. The thing we claimed earlier was more singular. And the log canonical threshold, therefore, appears to be maybe a better, more refined measurement of singularities than just the order was. So these integrals, I know how to compute them, and I'm actually going to show you how to compute them because it uses my favorite theorem that I told you about yesterday. But I have an exercise for analysts. I'm curious, I'd like to see how to compute this directly. I mean, how would an analyst compute these intervals and figure out what is the lambda needed to make this converge? But let me tell you how I can do it. How do you compute the integral? And actually, I think this is very interesting to analysts who might often need to compute intervals like this. So we already discussed a little briefly, sorry if I'm going a little bit fast, I'm trying to make up a little bit of time. We already discussed that we know how to compute this kind of integral using Frobenius theorem when we have a monomial. When our f, our hypersurface f is just defined by a monomial in the complex coordinates z1 through zn. And the idea is to try to generalize this fact we know from one variable complex analysis. So in one variable complex analysis, if I have an analytic function, for example, a polynomial is an analytic function, and I take a power series, then the power series is going to start with some z to the a, right? Power series at the origin will start with z to the a plus higher order terms. And then I could factor out the z to the a, and I would have z to the a times some analytic function which does not vanish at the origin. So every analytic function in one variable can be broken down this way just by looking at a power series. And and in fact, that a, of course, is the order of vanishing of the polynomial. And so we can see in one variable that this integral converges specifically when lambda is less than 1 over the order of f, 1 over a in this case. So the question now is whether we can somehow do the same argument in many variables. So let's make a definition. An analytic function will say it's locally monomial at a point if we can choose analytic coordinates for Cn near that point so that we can factor f like a monomial, like we just did a moment ago. So if I look at a power series of that complex analytic function in n variables, can I choose coordinates so that it's just monomial times a non-vanishing complex analytic function? So, of course, analysts and maybe others who've recently taken complex variables know that the answer to this question is definitely no. It's definitely not true that an analytic function in many variables will be locally monomial. Like the one-dimensional case is very, very special. Not even true for this cone. But the amazing thing about Hironaka's theorem that I discussed yesterday, and you don't need to remember that, I'm going to tell you again in a different version that might look quite different. Hironaka's theorem allows us to locally monomialize any analytic function or any polynomial is what we're interested in, any polynomial in this case. So let me state that theorem. So every polynomial function over the complex numbers in n variables has a local monomialization. So if I have a polynomial function on Cn, I can always find sort of a change of coordinates. This is not just a linear change of coordinates. This is some other complex manifold here. It's actually a smooth complex variety of the same dimension such that when I look at the pullback of that function, so I consider the composition, f is a function on Cn. I look at the function, first apply pi, then apply f. This is a locally monomial function on x. So if I choose local coordinates on x, then I can factor f. That's kind of an amazing fact that we can always do this for any polynomial function, or actually, in fact, any analytic function. So this is a theorem of Hironaka. He got a Fields Medal for it, and it's in some sense the same theorem I told you yesterday about resolution of singularities for varieties, although it's maybe not so clear from the current statement. But Hironaka's theorem on local monomialization tells us even more. It tells us not only can I locally monomialize the function f, I can also locally monomialize the Jacobian of this map we wrote down pi. Because you remember when we want to compute the integral of any function, right? And we try to pull back and do it on some other space. If you've taught Calc 3 lately, you remember that you need to multiply by the Jacobian. The Jacobian of the map comes into that procedure. This holomorphic Jacobian, when I take its norm squared, I get the usual real Jacobian R2n. And so this is just a fact that if I want to compute this integral, if I find a local monomialization, I can instead compute this integral. And this integral, everything's monomial, and it reduces me to the computation we did earlier. Then we can use the properties of this map to do this sort of thing on some finite number of charts and compute the log canonical threshold from that. So this is actually how I know how to compute the log canonical threshold of those cusp singularities we were looking at before. And an interesting consequence of this is that the log canonical threshold is always a positive number, because we can just get it from these monomial charts, the charts where everything is monomial. So I realize that this is a little bit complicated for people to understand in a colloquium talk. It's not that important to understand exactly what's going on here. The important thing, the important message of this is that this log canonical threshold is closely related, computing it is closely related to Hironaka's theorem for resolution of singularities, or at least its computation can be computed from a resolution of singularities. So on this page, I'm telling you a monomialization of the cone. And you see, this is the map. Here's the map from, this is a chart of the space X from before. So Cn, here's the map. And if I pull back F is my polynomial x squared plus y squared minus z squared. It becomes factors. And what I'm drawing in the picture is the zero set of the pullback of F. We see the cylinder, which is our resolution of singularities of the cone. And then we see this other yellow plane, which is the zero set of z, or really z squared here. And that's telling us, that's part of the local monomialization here. But we see the resolution hiding in this local monomialization. So yeah, that's what is going on in computing the log canonical threshold. Okay, but now the big question is, what about prime characteristic? So we talked about yesterday that we can look at varieties, not only over the complex numbers, but over any field. And so, for example, if I take a polynomial in n variables over a finite field, or over the algebraic closure of a finite field, perhaps, if it has n variables, I can still look at its zero set. And when I look at its zero set, I'll get a hypersurface in Kn. Instead of in Cn now, we're in Kn. And we can talk about the singularities or smoothness of points on a hypersurface over any field. We talked a little bit about how to do that yesterday. And so if I take a point on this hypersurface, I can ask how to measure its singularity. We can, of course, take the order. The order will still make sense. But can we do something similar to that log canonical threshold? We'd like to be able to do something similar to that log canonical threshold, which is also called the analytic index of singularities. So, of course, the problem is that when we're working with an arbitrary field, we don't have real analysis. We don't have epsilon balls around our point. We can't look at the volume under the graph. There's no integration. There's not even a good way to view necessarily a fractional power of the function g, which is what we were doing when we were looking at the log canonical threshold. So this seems like an insurmountable problem to try to define an analog of the log canonical threshold. But that's what I want to tell you about. It is not. We can actually do it. And so let me just put the punchline here before even telling you how to do it, because I'm worried about the time. And I think you only have to understand the fact that it can be done to appreciate it, I think. So if I take any field of characteristic P, so we're not over R, we're not over C, no, we're now over a field of characteristic P, such as a finite field of P elements or its algebraic closure. There's many other examples, but those are two. I take a polynomial and I take a point on it. I can define a numerical invariant of that point. It's called the F-pure threshold. And it basically satisfies the same properties as the log canonical threshold. So we observed that the log canonical threshold is a number that tells me how bad the singularity is. It's 1 at a smooth point, and it's smaller than 1 for very singular points. We also saw that the F-pure threshold, that the log canonical threshold could be 1 even when the hypersurface had some singularities, but they were mild singularities in a suitable sense. And that's exactly the same thing that we're going to do in characteristic P now, is we're going to define a numerical invariant of singularities that is going to behave like the F pure threshold, but like the log canonical threshold. So what do? We threw away integration. We threw away integral, delta epsilon neighborhoods and balls and all the good stuff of analysis. So we had to go to our tool that we talked about last time, which is the Frobenius map of a ring of characteristic P. So the Frobenius map of a ring of characteristic P is the Pth power map. The Pth power map, in general, if I have an arbitrary polynomial ring, like let's say over the real numbers, this would not be a ring homomorphism, because when I raise f plus g to the p and I expand it out using the binomial theorem, if I were over the real numbers, I would not have that f to the p, f plus g to the p is equal to f to the p plus g to the p. But this is exactly what happens in characteristic P. All the binomial coefficients are divisible by P, so they all become 0 in characteristic P. And so this tool is our tool that we replace all of the analysis by. And it's kind of remarkable that we can do that. I want to show you, for example, that remember when we were talking about real valued functions, the norm of f, we raised it to some fractional power. The Frobenius gives us a way to do that in characteristic P. So let's explain that. I want to explain how to interpret a rational power of a function of a polynomial. How we define a rational power. So we can't define or real power, actually. We want to define any power, but we can't actually define it for all rational numbers or all real numbers. We need to take only rational numbers whose denominator is a power of P. Now, every real number, if you think about just like a base P expansion of a real number, let's say a real number in between 0 and 1, it always has a base P expansion. So if I truncate it at various stages, I will be able to approximate any real number by a rational number whose denominator is the power of P. So what we're going to do is we are going to define G raised to such a rational number. So the Frobenius map is a ring homomorphism. And so it gives us an isomorphism onto its image. The image of a ring homomorphism is always a subring of the target ring. In this case, in the Pth power map, we'll get the subring generated by all the Pth powers in the ring. In other words, you can think of it as the polynomial ring over Fp in the variables x1 to the p, x2 to the p, and so forth. This is an isomorphism because it's surjective onto its image, and there is no polynomial in the kernel. When I raise the polynomial to the Pth power, I will never get 0. So the kernel is 0, the image is this ring of Pth powers, and so we have an isomorphism. Basically, what this tells me is I can take a Pth root of any element. If I want to take the Pth root of a polynomial G, I instead think of it as a Pth power of something, and then in this other ring, and it's now a Pth root. So this gives me a way to define a unique Pth root for every polynomial. And so, for example, to define the power G raised to the A over P, I would just take the P to the Eth root of the polynomial G raised to the A. Okay, the point is for polynomials in a polynomial ring of characteristic P, I can take P to the Eth roots for any E. And this is something that's actually very popular right now in algebra, to study this ring where I've thrown in all the P to the Eth roots. This is called the perfection of a ring. Okay, so let's try to do a similar thing to what we did before. Before we had a complex polynomial f, and we considered the growth of fractional powers as we approached the singular point. And now what we're going to do is look at a polynomial degree P of characteristic P. And what I've done here is just wrote two variables because it fits better on the screen. But this can be in any number of variables. And we want to study the growth of G raised to the lambda. And we can only do that when lambda is A over P to the E. So we interpret G to the raised to the A over P to the E as an element in this perfection ring. And we want to ask how fast G to the lambda approaches zero near zero. It doesn't make sense because we don't have real analysis to talk about something like that. But the next best thing we can ask is for what values of G to the lambda is G to the lambda in the ideal of functions that vanish at zero. And it turns out that for larger values of lambda, G to the lambda is always in the ideal of functions, the ideal generated by xy, those are the polynomials that vanish at zero. And for smaller values of lambda, it never is. And so there's some cutoff point again. There's some cutoff point where G raised to the lambda is in the ideal M for larger values of lambda and not in for smaller ones. And this is the F pure threshold. So I know that's hard to understand if you're not an algebraist, but the point is I'm trying to get across is this somehow has a similar flavor to the way we define the log canonical threshold. Some kind of fractional power of our function of interest, and then some kind of cutoff where that fractional power has certain behavior. Okay, so here I just repeated the definition for you in a slightly different way, so that algebraists might stare at it in a more compact form. This is something that can be computed pretty easily on a computer, at least in low degree examples and so forth. And many people have done some. I'm going to show you some cool pictures in a few minutes. But in any case, in this example, I'm going to look at the same cusp. So remember, we looked at this cusp singularity before. I should have drawn a picture of it again on this slide. But this was that nice cusp that we looked at before. Y squared equals x cubed, the vanishing set of y squared minus x cubed. The F pure threshold of this at the origin, at the singular point, now depends on P. So this is interesting. It is smallest when P is 2. So somehow this curve is the most singular when we're in characteristic 2. It is slightly bigger when P is 3. So if I look at that same cusp curve, it will be slightly less singular in characteristic 3. And then in higher characteristics, what we see is it is approaching the number 5/6. And 5/6, maybe you remember, that's 1/2 plus 1/3. That is the log canonical threshold of the curve, the cuspidal curve, y squared equals x cubed, when I think of it as a complex curve. So this is interesting. We're getting something very similar to the log canonical threshold that in fact is approaching the log canonical threshold as P goes to infinity. So on the next slide, I'm just summarizing again some of the properties of the of the F pure threshold. These are all similar to, in fact, these are all the same statements for the log canonical threshold. So maybe I should just have called this properties of the singularity index. And that singularity index is either the log canonical threshold if I'm talking about complex hypersurfaces, and the F pure threshold if I'm talking about hypersurfaces over fields of characteristic P. And we see that this is a number which measures the singularities. More singular points are going to have smaller F pure thresholds or singularity indices. Now, one theorem that wasn't stated earlier for the F pure threshold, but we did observe it quickly for the log canonical threshold, is this number, this cutoff is always a rational number. And that's a theorem by myself and Manuel Blickel and Richard Mastada. I think it's definitely not clear from the way we defined it as a supremum. Okay, let me give you a formal one careful statement of the relationship between these singularity indices over the complex numbers and over finite fields. So if I take a polynomial in n variables with integer coefficients, for simplicity, this works for arbitrary coefficients, but let's think about integer coefficients for a moment. And I'm going to assume that when I plug in 0 for all the variables, I have 0. That's going to tell me that the origin is a point on the hypersurface defined by G. When I think of G as a polynomial over the complex numbers, or I could reduce the coefficients mod P and think of it as a polynomial with coefficients in FP. And when I do that, I can compute this singularity index for all of these polynomials, all closely related, right? I could take G mod P and compute the F pure threshold of that characteristic P polynomial, or I could compute the log canonical threshold of this complex polynomial. These are going to be numbers that tell me how singular the hypersurface defined by G is at the point 0, at the origin. And so what this theorem says, which is proved by this group of Japanese mathematicians, is that the F pure threshold is always bounded above by the log canonical threshold. So the F pure threshold might be smaller, but it could be equal to the log canonical threshold. So in characteristic, when we have a complex hypersurface, it's always somehow not necessarily quite as singular as what we would have if we reduced mod P. And not only that, even better, when I take the limit as P goes to infinity, I will always see that the F pure thresholds are converging to the log canonical threshold. So this singularity index over the finite field always converges to the singularity index over C. And it always does some from below, because singularities can basically only be worse in characteristic P than they are over the complex numbers. That's what this theorem is essentially saying. So here's a cute example for people who like elliptic curves. If I take the homogeneous polynomial of elliptic curve, so that's just a degree 3 curve in 3 variables. It's familiar to a lot of number theorists and algebraic geometers and students who have taken a number theory class. We can look at that homogeneous polynomial as defining a hypersurface in 3 space, because it's a homogeneous polynomial in 3 variables of degree 3. And when we reduce it mod P, what we see is its F pure threshold depends on whether or not the elliptic curve is what's called ordinary, which is most of them, or super singular, which is just not ordinary. I've put a little definition of ordinary here. There's many equivalent definitions. I'm sure you know a different one if you've, but I put one down. We're experts, but this is interesting. Again, we see as P goes to infinity, this number is approaching 1 in this case, and that in fact happens to be the log canonical threshold of that complex singularity defined by G. So here on this slide, I have some people. Bargoff Bott was the first person who observed this fact. He's my colleague at Michigan. But then Gilad Pagi was a PhD student of mine who gave a much simpler, straightforward proof of this fact. And then Anurag Singh here and Bargoff together wrote a paper later based on Bargoff's observation that holds more general. I think a similar thing to this holds for what are called Calabi-Yau. surfaces or varieties. Also, there's a student in Germany who's actually my grad student. It's a student of Manuel Blickel, named Suzanne Muller, who generalized this to quasi-homogeneous polynomials. So here's another picture I wanted to explain, which was on the first slide where my title was. This is again showing you ways in which the F-pure threshold, the singularity index in characteristic P, approaches the log canonical threshold. So these pictures were created by Daniel Hernandez and Pedro Teixeira, who are two of the people who are most expert in the world at computing F-pure thresholds. And these are representing F-pure thresholds of a particular family of plane curves. Basically, each point on this fractal surface is the F-pure threshold of a curve in characteristic 2. And if I look at the corresponding point over on this guy, it will be that same curve viewed in characteristic P. And if I look over on this one, it'll be the same curve in characteristic 5. And what we see is this fractal-like behavior as we go through the P's, but it's the prime numbers, but it is converging to some straightforward behavior as P goes to infinity. That's